Hi guys, Dr. Orlando here with a video on cell membranes. So today we're going to look at the components of the cell membrane and discuss the fluid mosaic model of cell membranes. So by the end of this you should completely understand what we mean by fluid mosaic. Okay. With fluid mosaic, fluid refers to the fact that the cell membrane is very mobile. The components of it are mobile. It's not solid like a fat. It's more like works more like an oil. And the mosaic part refers to the characteristic that cell membranes are made up of many parts, and we'll look at those parts. Okay, so let's look at this little guy I've drawn already. So you can see that the membrane, this is the membrane of a cell. So this would be the extracellular space or fluid. This would be the intracellular fluid. Okay, so you can see that so far in my membrane I've drawn phospholipids and I've drawn cholesterol. Phospholipids are a key component of the plasma membrane, and we'll look at their characteristics in just a moment. Cholesterol, also very important. Cholesterol, you can see that I've drawn just as 4 circles, but in fact it's 4 rings of carbon, and both cholesterol and phospholipids are lipids, so they add the lipid component of the plasma membrane. Okay, so let's look at a phospholipid in detail. Okay, so I've drawn 2 phospholipids here. So remember, with a phospholipid, the head, the circle that we draw, is, I'm going to make this blue actually, hydrophilic. While the tails, these guys here, are known as the fatty acid tails. They are hydrophobic. Okay, that makes them nonpolar, makes the head polar. Okay, and that's the same of this guy next door here, same thing. But let's look at what makes this head hydrophilic. Inside the head there is some positively charged, apositively charged nitrogen. Let's see if I can do that better. Sorry about that. Inside there we've got a positively charged nitrogen, we've got a negatively charged oxygen. So we've got charges, and we know that our friend water loves charges, right? Because water itself is polar and has a partial charge. So these hydrogens have a partial positive charge, the oxygens have a partial negative charge. We can draw this over here as well. Put the hydrogen there, oxygen, hydrogen. Drawing our charges. And then we can take some little dots and make them bond with each other. Remember, when we draw those little dots, we're usually representing hydrogen bonds. So you've got an electrically negative end of a molecule being attracted to an electrically positive end of a molecule. So that's why the head is hydrophilic, because of those charges that are in there. They are attracted to water, and water is attracted to them. The tails are different, though. The tails are made up of hydrocarbons, fatty acids. And remember, there is a glycerol backbone right in here that they are attached to. So this is where the fatty acid would be attached to that 3-carbon glycerol backbone. And then the fatty acid tail is made up of a chain of carbons surrounded by hydrogens. Remember, carbon can make 4 bonds, so these carbons that are in the middle are bonding with their carbon neighbors, and then have hydrogens to fill in the rest. Okay, so that is a lipid, a fatty acid, excuse me, and you can see that all of the bonds are single, so we say that this is a saturated fat. Okay, and notice that I drew it very straight, and I also drew the lines here that represent my fatty acids as straight. Okay, so them being straight is going to be important. Let's go and look at what happens if they're bent. So we'll go over and look at this guy here. Let's keep those like that. And we'll zoom in. Okay, so same thing is true for the head. This is going to be the hydrophilic head, polar, loves water, has the nitrogen and the oxygen in there. Let's look at the tail. Specifically, let's look at this one here. Okay, so that tail, if we were to draw it, would look like this. Okay, so now we'll draw in the hydrogens, and you'll see what happens here. Okay, so notice how I drew the double bond there, and the hydrogens here and here are on the same side. And when they do that, they create a bend. That double bond, by the way, made it so that we are missing a hydrogen here and here, right? Because carbon is sharing a double bond with its neighbor, so it doesn't need extra hydrogens. So we say that this one is unsaturated. And this actually makes it more like an oil, so it's going to be fluid. Why is that? Well, the more double bonds this has, the more kinky it is. It creates these bends, and those bends do not stack very well. If you look at, if you go over here, and you pull this way, if we were to have a whole bunch of these guys, they would stack really nice like that. Their fatty acids would stack like that, and that would be a solid. Okay. If we have fatty acids that are different, though, and have little kinks in them, you're going to end up with a stack that is not flat and kind of messy, and therefore they don't stack together. They become a liquid. So saturated fats are solid at room temperature. Oils, unsaturated fats are liquid at room temperature. And certainly in the body, we're above room temperature. So having these in our plasma membranes makes the plasma membrane even more liquidy and movable. So let's go back and look at our plasma membrane. Okay. Alright, so I drew all these fatty acids in here with their tails all kinky and funny looking, and I put the cholesterol, inserted those into the plasma membrane as well. Cholesterol is interesting. It helps with both ends. It helps keep the membrane more fluid, and it also helps keep the membrane more solid, so depending on the temperature. If it's really warm out, cholesterol kind of stabilizes the membrane so it's not too oily. If it's very cold, then it will help keep the membrane still being very fluid. Okay. All right, so we've got cholesterol and we've got the phospholipids. Next up to talk about in the membrane is going to be the protein component. And I'm not going to go into all the details of the proteins. That'll be a separate video, but let's just draw in some some proteins here. Proteins, I'm going to make them purple. So I'm going to erase a little bit. Proteins are throughout the membrane, and they have many different jobs. Okay, I'm going to just draw, kind of give them a little bit of color there. Put one there, put one here. Can make them different shapes. And remember, proteins are made up of amino acids, and the amino acids have those side groups which give each amino acid a unique property, and it will end up at making a protein that has a unique shape. And with proteins, shape is very, very important. Conformation is very important. So the protein made up of the amino acids and very specific shape. Okay, and then that shape determines its job. And again, like I said, we'll talk about that in another video. Some of these proteins will have, they might have be like a channel, like I'm drawing here, for things to go through. Okay, some of them might have sugars. Let's get a new color here. They might have sugars hanging off of them. We'll do this one here. Branched chains of sugars. Okay, and maybe they're there for recognition or something like that. So let's write that in. We've got sugars, we've got proteins. Oh, we can even draw some of these proteins like little rafts. Should put one up here, floating along. Okay. Some of them go through the membrane. Some of them sit on top of the membrane. Okay. So there's our mosaic. We've got lots of different components here. We've got the phospholipids, we've got cholesterol, proteins, sugar, all making up our plasma membrane. And that is the mosaic portion of fluid mosaic. All right, if you have any questions, feel free to give me a call.